In this short video, we're going to show that a differentiable function is continuous. In particular, if f is differentiable at a single point, then it is continuous at that point. And then, of course, you can generalize that to all points. So we're going to have a function from c to c. It'll be differentiable at a point z in its domain. Actually, the function doesn't need to be defined on all of c for this to be true. It can be defined on a much smaller section, but I'm just simplifying here. So we'll show that we're not going to show continuity directly. We're going to calculate the limit as w approaches z of f of w, and we need to show that that limit gives you f of z, which means that the limit as it approaches that is equal to the value, which means that the function will be continuous at that single point at least. So this proof is surprisingly easy. And so we're going to calculate the limit of f of w as w approaches z. Now, we don't know that this limit exists, but if we can calculate it by appropriate limit laws that guarantee its existence, then we'll be okay. So we're going to take this limit and we're going to subtract f of z. Now, what do you think we're going to get? I need to show that we're going to get 0 here, right? Because I've claimed that the limit is equal to the value. And so the limit minus the value is supposed to be 0. So I'm going to sort of try to calculate what this is. And if I can get 0 out of this calculation, then I will have shown that if I can get 0 out of the calculation and get a calculation which justifies the existence of the limit, then we'll be all set. So now this is a constant from the point of view of the approach of w towards z. And so I may write this as the limit as w approaches z of f of w minus the limit as w approaches z of f of z. And this is equal to the limit as w approaches z of f of w minus f of z. So these two limits either both exist or both fail to exist because they differ by a constant value. So, okay, what good is that limit? Well, now I'm going to complicate matters even further. I'm going to multiply and divide by w over z. So we'll have some opportunity to question whether this is valid because it looks like I may have introduced an error, which we'll come back to. So f of w minus f of z over w minus z times w minus z. These two limits either both exist or both fail to exist because they are exactly the same limit, because this function is the same as this function. And now you're saying, but wait a minute, this function is defined when w equals z, and this function is not defined when w equals z. And so there is a slight difference in the domain of those functions. In particular, this is a function of w which doesn't exist at, this is a function of w that doesn't exist at z, and this is a function of w that does exist at z. And yeah, okay, that's true, but the limit never references the point w equals z. That's sort of the point of the limit. It ignores the value there. And that's, if you look closely at the definition of the limit, that's this business about the distance between w and z being strictly greater than 0 at the same time that it's strictly less than delta. That guarantees that that point is never actually considered. So for the purposes of the limits, these two functions are equivalent. Okay. Now I'm going to calculate this limit by splitting it by the limit laws. Now, does the limit law apply here? I haven't even proved yet that this limit exists. I'm questioning whether this exists. But the limit law says if the right-hand side of the application of the limit law exists, then the left-hand side does too. And so, so long as I eventually compute an answer by limits that do exist, then after the fact, the use of the limit law will be justified. So what does the limit law say? We're going to apply the limit law for the products, which is one of the reasons why we worked so hard to prove it. We're going to get the limit of f of w minus f of z over w minus z, and that's supposed to look familiar, times the limit as w goes to z of w minus z. So this guy is supposed to ring a bell. If it doesn't, please review. That is the definition of the derivative. Now, all the while, we've been questioning whether these limits exist. Do we have any reason to believe that the derivative exists? Well, yep. Right? We have assumed that this function is differentiable at that point. And so that constitutes the assumption that this limit exists. So this is, by definition, f prime of the point z. Do we have any reason to believe that this limit exists? Well, yes, this is a very simple limit as w approaches z of w minus z. As w approaches z, w minus z goes to 0. So this limit exists. So this limit exists because I can just calculate it and it's easy. This limit exists because I have assumed that it exists. Because they both exist, the application of the product law for limits was correct indeed and justifies that this limit exists, and therefore so does this one, and therefore so does this one. Not only that, but we've computed the value. So what we can conclude here, this is something times 0, so we get 0, and thus thus the limit of, as w approaches z, of f of w is equal to f of z, because their difference is computed to be 0. And it follows that f is continuous at the point z. And this demonstrates that if a function is differentiable at a point, then it's also continuous at that point.